So today I'll be presenting on childhood obesity, early childhood caries, and the oral microbiome. It was a secondary biostatistical analysis project on ZO 2.0, which I'll explain to you later. I was co-advised by Dr. Di Wu and Dr. Kimon Devaris. And first, I want to start off with some acknowledgements. First, my two advisors, Dr. Wu and Dr. Devaris, from the Department of Biostatistics and the School of Dentistry, and their two graduate students, Hunyang and Meredith, who were great support for this project. In this presentation, I will be going over some background information, objectives, methods, results, and some limitations and future directions of the project. First, I want to go over some background information on childhood obesity. Childhood obesity is one of the most prevalent conditions in the United States, caused by an imbalance of energy intake and expenditure. And it is measured by the body mass index, or BMI. In children, BMI levels are expressed relative to other children in the same age and gender group because their body composition varies with age and gender. Children in the 95th percentile among the same age and gender group are considered obese. Childhood obesity has been a growing concern in the United States. As you can see on the graph on the right here, this graph was adopted from the 2018 National Health and Nutrition Examination Survey, and it reported that 19.3% of children in the US of age 2 to 19 years are obese. This is about 14.4 million children and records about a 5% increase in the 20-year period. Childhood obesity increases the risk of non-communicable chronic diseases in children, including high blood pressure, high cholesterol, type 2 diabetes, breathing problems, and joint problems. Obese children are highly likely to be obese adults, which increases their risk of chronic diseases, cardiovascular diseases, and cancer in later years. Early childhood caries, or ECC, is another prevalent condition in the US, defined as the presence of one or more decayed, missing, or filled tooth surfaces in any primary tooth in a child under the age of 6. It is caused by the disrupted balance of demineralization and remineralization at the tooth biofilm interface, where the microbiome ferments carbohydrates and produces acid. It is measured and classified under the International Caries Detection and Assessment System, in short ICDAS, where an ICDAS level of 1 or higher is considered sensitive, and an ICDAS level of 3 or higher is established or severe. The role of oral microbiome in these two conditions have been investigated in multiple studies, and has been clearly revealed that oral bacteria gives rise to dental caries with its metabolic activities. In childhood obesity, however, there have been conflicting opinions on the role of microbiome. Ben Ahmed et al. Suggested that the oral microbiome is only implicated with childhood obesity with its modulating effects on the gut microbiome, which plays an important role in metabolism and ultimately the development of obesity. Craig et al., however, suggested that the oral microbiome can serve as a stronger indicator of infant weight gain than the gut microbiome. We extended on this idea to explore the potential of oral microbiome as an indicator of childhood obesity, and we also explored the potential of oral microbiome as a common biomarker for childhood obesity and early childhood caries. We used an existing data set from ZOE 2.0, which was conducted by Dr. DeVaris and Dr. Wu and their colleagues. It's a genetic epidemiological study of oral health in children of age 3 to 5 years enrolled in Head Start centers in North Carolina. There were 8,059 subjects enrolled, but only 6,404 subjects with clinical dental data. It includes data of demographic and clinical. It includes demographic and clinical data, which includes family history, current oral health status, and environmental factors. And for a subcohort of 302 subjects, it includes the oral microbiome data, more specifically the DNA and RNA sequence data from the oral biofilm sample, samples. Statistical analysis was performed on the subcohort of 302 subjects. 4 subjects were excluded from the DNA analysis, and 7 subjects were excluded from the RNA analysis due to age and ineligibility, lack of phenotype data, lack of or low RNA sequence data, and a lack of BMI data. A total of 6,412 bacterial species were identified from the oral biofilm samples, but low prevalent and low abundant species were filtered out, resulting in 666 core species, which includes 418 DNA core species, 632 RNA core species with an overlap of 384. 4 multiple linear regression models were run on the sequence data, and all models accounted for age, gender, and sequence batch. I'm sorry if this is a lot. I'll explain the variables later in a second. But model 1 investigates the relationship between obesity and the individual species. And models 2 and 3 are the same as model 1, but stratified for the presence of ECC. This means that model 2 only includes the samples or the subjects that did not have any ECC, and model 3 only includes the subjects that had ECC. Model 4 studies the relationship between the presence of dental caries and each microbial species. Here are the variables used in the models. Z-BMI is a continuous variable of Z-score transformed age and sex-adjusted BMI. As you can see on the right, it is normalized. And species is a continuous variable of DNA and RNA sequence reads, normalized in transcripts per million for the individual bacterial species. Age is a continuous variable in months at the time of the exam of the subjects. Gender is a binary variable of genetically verified gender, boy or girl. Batch is a categorical variable of the identification numbers for each sequencing batch. And finally, T6 is a binary variable of the absence and presence of established or severe dental caries based on the international standards. Each linear regression model was run with DNA and RNA sequence data, and the p-values and the coefficients were extracted from each model. The p-values were adjusted using the FDR method to account for any effect coming from using multiple covariates. The lists of significant species from each model were compared to elucidate the role of each species in childhood obesity and ECC. Here are the results from the linear regression models. The models are explained in the left bottom corner for your reference. And species were identified as significant with the nominal p-value less than 0.05, but we focused on the species that had an adjusted p-value less than 0.2. There were 75, 26, 78, and 31 significant species identified in each model, models 1 through 4. And there were 5, 0, 29, and 11 species with an adjusted p-value of less than 0.2 for each model. There were some overlaps between the models, resulting in a total number of significant species across the 4 models of 167, 146 of which were obesity associated, and 104 of which were associated with both conditions. The significant species were divided into 4 groups. And the first group here in the region highlighted in red were associated with obesity only in the absence of dental caries. There were a total of 25 species total, 16 of which showed a positive correlation with BMI and 9 of which showed a negative correlation. A positive correlation means that more prevalent these species are in the oral biofilm, higher the risk of obesity in the absence of ECC. And the negative correlation means more prevalent these species are, lower the risk of obesity. Here are the species that are associated with obesity only in the presence of caries. The total of 77 species, 30 of which were positively correlated with BMI, and 46 of which were negatively correlated. One species was excluded from the count because it demonstrated a positive correlation in the DNA analysis and a negative correlation in the RNA analysis. There were 24 species in this set that with the adjusted p-value less than 0.2. And an interesting phenomenon to note in these 2 groups was that the direction of correlation, positive or negative, changed in some of the species with the stratification. For example, one species had a positive correlation with BMI in model 1 where there was no stratification, but it demonstrated a negative correlation to BMI when it was stratified for the absence of ECC. The statistical and biological significance behind this phenomenon is yet to be explored. So we focused on the groups that I'm about to show you now. Species in this group were only associated with obesity and showed no ECC association. The one species in the small region highlighted in red was included in this group because it showed association to obesity, both in presence and absence of ECC. There were 42 species in total, 23 of which were positively correlated and 19 of which were negatively correlated. 2 species had an adjusted p-value less than 0.2, which are Glycerella species 15-814, which was negatively correlated, and Actinobacillus pleuropneumoniae, which was positively correlated. This means that a lower number of Glycerella and a higher number of Actinobacillus would increase the risk of childhood obesity. Last group of significant species. There were 2 species that were associated with obesity and ECC on separate terms, one of which had an adjusted p-value less than 0.2. Veillonella dispar was negatively correlated to both obesity and ECC, which means that the more prevalent the species is in the oral biofilm, lower the risks of obesity and dental caries would be. In conclusion, Glycerella species 15-184 and Actinobacillus pleuropneumoniae may potentially serve as an indicator of childhood obesity, and Veillonella dispar may potentially serve as a common biomarker for childhood obesity and early childhood caries. Other species need further analysis for conclusive results. Well, the limitation of this study was the limited sample size, resulting in limited testing power. Although the sample used in this study was the largest cohort that has microbiome data of biofilm samples for children of age 2 to 5 years, larger samples could improve the testing power. Subsequent studies could explore the contradicting directionality of correlation from the stratified sampling and the biological mechanisms of identified species and their roles of childhood obesity and ECC. Finally, the metabolomics of the oral biofilm with regards to the 2 conditions could also be explored to identify any metabolites that could serve as a common biomarker for the 2 conditions. Here are the references, and that's it. Thank you.